Alright, this is Waves Review Part 2. So this one starts on number 11. Number 11 says, if a wave bends toward the normal as it goes from one medium into another, did it speed up or slow down? If it bends toward the medium, so let's just say that we have a medium here, and we have a wave, the normal drawn, normal is at 90 degrees to the medium, and we have a wave enter. If it bends towards the medium, then it's slowed down. So towards, V goes down. Away means V goes up. So if the velocity goes up, it means it bent away from the medium. If the velocity goes down, it means it bends towards the medium. Okay? Or sorry, not towards the medium, towards the normal. Okay? So if it goes away from normal, the velocity is going up. If it goes toward the normal, the velocity is going down. Alright? That's number 11. Number 12. What phase difference results in maximum destructive interference? Well, this is where you would have maximum destructive interference occur, and this is 180 degrees out of phase. Least destructive interference would occur whenever they look like this, when crest meets crest and trough meets trough, and this is 0 degrees out of phase. So 180 degrees out of phase, max destructive interference, 0 degrees out of phase, minimum destructive interference. Let's see, number 13. Draw a representation of a 170 Hz standing wave in a tube that is 2.5 meters long and open on one end. Well, the first step that we need to do here is we need to do V is equal to lambda F to calculate the frequency, or rather the wavelength of our wave, because we need to know that, and the speed of sound is what our velocity is going to be, and that's equal to lambda F. And F is 170 Hertz, so lambda equals 2 meters. Now we need to draw the wave. Well, inside our tube that's 2.5 meters long, we need to have at least a 2 meter long wave. Alright, so we need to have this 2 meter long wave drawn. So what I'm going to do is I'm going to mark out where 2 meters is. Let's just say that's where the 2 meter mark is. We're between the red lines, and we're going to make a 1 wavelength in that space. Okay? Oops, sorry, hang on. Back up a little bit. Alright, so this is our 2 meter long wave right there in this little spot between here and here. We have our 2 meter long wave. Now it's got to finish out the rest of the thing. This is convenient because you'll look, a quarter of a wavelength would start right here, and that would be half of a meter. So we keep drawing another quarter of a wavelength for that last half of a meter, and we get a shape that looks like this. Please forgive my drawing, but the quarter of a wavelength, each quarter of a wavelength here should be half of a meter, so that you should have a full wavelength from here to here, and then a quarter of a wavelength more. Okay? That's number 13. Number 14. What are the conditions for resonance to exist? Well, you have to have forced vibrations. Then it can either be forced vibrations that you force it by hitting it, or sound moving something and causing it to vibrate. So we have in the wine glasses, if you'll remember, with the wine glasses we had two examples. We had rubbing the finger along the edge, like in the Miss Congeniality movie, or singing into the wine glass and using your voice to break the wine glass, like we saw in the Mythbusters video. Alright, probably both of those you can find on YouTube if you want to just do a quick search for those two examples. The other two were whenever we did the tuning forks. That's another example, tuning forks. And the other example is the balloon with the ribbons that said some things. Sorry, not balloon over ribbons, just balloon with ribbon. Alright, so those are your examples. Next one we have what determines the speed of a wave, and that is the medium. The medium determines the speed of a wave. Alright, so I'm just going to erase that. I'm not going to waste this page on that. But the medium is what determines the speed of a wave. If the medium changes, the speed has to change. And please remember that if it changes mediums, it normally refracts. Alright, let's see. Next, number 16. This is a tad bit tricky, so please try to stay with me, alright? Here's what happens. Okay? Now, the horn is attached to a car. So I'm just for the sake of ease, I'm going to draw a circle to represent the car. Now the car is emitting sound. Alright? Now, the car is moving while the sound is being emitted. So, what's happening here is the velocity of sound is 340 meters per second. The velocity for the car is 80 meters per second. Alright? Now, as the speed of sound, as each wavefront leaves the car catches up a little bit. So if a second went by, instead of being 340 meters away, like it should be if it was stationary, the car is now only 260 meters away. So from the wavelength's perspective, from the car's perspective, the wavelengths are only leaving it at 260 meters per second. So what that does is it shortens the wavelength because the car is catching up to the sound. So for the car, the speed of sound appears to be 260 meters per second. And so if the frequency is 100 hertz, then that gives us a wavelength that appears to be, the car appears to be emitting a sound with a wavelength of 2.6 rather than the 3.4 that it would have normally been emitting. So this is our wavelength that's perceived. So if you're standing here, you perceive the wavelength as 2.6 hertz. But for you, since you are not moving, the speed of sound for you is 340 meters per second still. So, but you're picking up on this wave that's coming into you at every 2.6 meters. And so we want to find F. Well, you divide 340 by 2.6, and when you do this, you should get F is 130 hertz. And so since this object is coming towards you, its original frequency was 100 hertz. Since it's coming towards you, it now increased to 130 hertz because of the fact that the car was catching up to the sound wave. Okay. Number 17. What is the shape of a straight wave after it passes through a slit in a barrier? Okay, so a straight wave, first of all, is just a wave front. Here we have our barrier. Here we have our wave front. So it's coming in. Imagine just like an ocean wave coming into to some kind of barrier built up, maybe a bay or something. What happens is when the wave passes through the barrier, it gets diffracted around the barrier. It starts to bend around the barrier like that. Okay, so that's the way it would look. Alright, then we have number 18. What are the two ways of getting energy from one place to another? That is a particle, like if you throw a ball at somebody, and a wave. So we have particle and a wave. Those are the two examples. What evidence have you heard that would convince you that sound is a wave? Well, we've proven that waves reflect because of an echo. Sound waves will diffract. We proved that by, me talking under the table, talk around corners. We've proved that sound is a wave because I have been able to, produce the Doppler effect. Okay, by doing the annoying ball. Okay, so these are three ways that I've proven that sound is a wave. All right, and the last question. What is a polarized wave? A polarized wave is a wave that is only traveling in one direction. Okay, only travels in one direction. If you have an unpolarized wave, a wave that is going in multiple directions, all right, and you want to polarize it, well, then you just put it through a filter like this, and when you put it through that filter, it will allow waves to only go through in a single direction. All right, and so it will take this kerfuffle here and make it into one direction. All right, if you have any questions, feel free to tweet me, and I will try to get back to you. Sorry this is a little late.